Welcome everyone. In this video, I am going to discuss a problem on Riemann mapping theorem. I have given a bounded and simply connected domain omega, and the function g is an analytic function defined on this domain omega. What you have to prove is, you have to prove that if this function has two fixed points, then it should be an identity function. Okay? Right, so let's go to the solution. This is my simply connected domain, simply connected and bounded domain omega, and it has two fixed points, A and B. That means these 2 points are invariant under this function g. Okay, so that means if you apply g to A, you would get A. If you apply g to B, you would get B, because they are fixed. Okay, right. Then from the Riemann mapping theorem, I know that I can map any simply connected domain to the unit disk if it is not equal to the whole complex plane. But in this case, my domain omega is bounded, so I'm sure that it's not the entire complex plane, because complex plane is unbounded, but omega is bounded, so it's clear that omega is not equal to the whole complex plane. So I can map this omega to the unit disk through some conformal map, and this omega, the image of omega under this function phi is going to be the unit disk. Okay, so phi is a conformal map that maps this domain omega onto the unit disk. Okay, and this map is unique if I map A to 0 and if the derivative of A is positive. Instead of A, I can pick any point, but in this case, I'm going to select point A. Okay, because it is kind of important point for me. Okay, right. So this phi would map A to 0, and then phi would map A to 0. I can define the inverse of phi. So inverse of phi map 0 to A. So what does this map do? This map would map 0 to A, and under G A would be mapped to A, and under phi A would be mapped to 0 again. Okay. So if you consider this composition would map 0 to 0. Okay. Let's see why it's true. So if 0 is phi compose G compose phi inverse 0. So phi inverse 0 is going to be A, and GA is going to be A because A is a fixed point of G, and GA is A. So phi A would be 0. Okay. So F0 is 0. So I can use Schwarz Lemma now, because I know that capital F is a map from the unit disk to unit disk. Capital F is an analytic function from unit disk to unit disk, and F0 equals 0. Okay, right. But I can notice another property of this capital F, that is, now first I applied 0 for this function capital F. Now you can notice that the point B is in this domain omega. So what can you say about phi of B? If you apply the function phi to B, you would get some point in this unit disk, and it cannot be 0, okay? Because this is conformal. A is gonna map to 0, then B would be mapped to some point that is different from the origin, okay? Right. So now instead of 0, I would apply phi B to this capital F, okay? So, right, let's see what would happen if I substitute phi B instead of Z. Okay, for phi B, so this is going to be phi compose G compose phi inverse phi B, but phi inverse phi is identity, and identity of B is B. So I would get phi compose GB, but what is GB? B is a fixed point of G, so GB is going to be equal to B. Okay, so you can notice that if you apply the function capital F to phi b, you would get phi b back. Okay, so phi b is another fixed point of this capital F. Okay, so we notice that the capital F has two fixed points. One of them is 0 and the other one is phi b. Okay, so I can claim that capital F is an identity function on the unit disk. This is how I prove that. I know that f0 is 0, if phi b is equal to phi b. So from the Schwarz lemma, since there are two fixed points, I can say that fz equals z e to the I theta. But I can plug phi b to the function, and then I would notice that e to the I theta is going to be 1. So what would I get then? If z is equal to z, okay, that means capital F is an identity function from unit disk to unit disk. Okay, right. But what is capital F? We know that we notice that capital F is this composition. Okay, so this composition is going to be equal to the identity, and I would get phi compose G compose phi inverse is identity. Then I would do the right composition by phi, then I would get phi here, and left composition by phi inverse, then I would get phi inverse there. Okay, so if you compose any function with the identity, you would get the same function. So identity composed with phi is phi. So at the end, I would get G equals phi inverse compose phi, which is equal to the identity. So now I can say that the function G is going to be the identity function. Okay, right. So this is a good problem on Riemann mapping theorem and Schwarz lemma. I hope you all understood what I did. If you have any questions, you can mention them in the comment section. And thank you for watching.